Okay, recording has started, so good afternoon, everyone. Today, we're going to start chapter 5, which is exciting because I think that chapter 5 is one of the more fun parts of this class. So basically, up until now, we have been slogging through all of this derivative stuff and trying to understand how functions are changing, how do we interpret the ways that functions are changing, how do we estimate functions using their rate of change, and all of these applications of derivatives and all the rules of how we take them, right, and the shortcuts of how we do derivatives, right? And now we're going to switch focus and talk about the other part of calculus. So there's derivative calculus and then there's integral calculus. So you can loosely think of integral calculus as a process by which we are sort of going to do the reverse of what we do with derivatives. So with derivatives, we have a function which describes maybe like an amount of a substance, right? Could be money, could be distance, could be bacteria, or whatever you want, right? And then we take the derivative of it to understand how is it changing. And what we're going to do now is kind of the reverse of that. We're going to start with a function which expresses how something is changing, the rate of change of something. So we start with the derivative of a function. And then we're going to ask big questions about, well, what is happening to its parent function, i.e. The amount function, right? So that is kind of where we're going with chapter 5. I'll say more about that in a minute. But just a couple announcements really quick. There is a homework due today. At midnight. It's 20 questions long. There's also another homework that I posted just this morning, which will be due on April 12th on 5.1 and 5.2, which is what we're going to do today and on Thursday. There's also going to be a quiz on this Thursday covering sections 4.3 and 4.4 and 5.1, which we'll do today. So if you want some practice on those 5.1 problems before we take the quiz on Thursday, you could try out some of those problems from 5.1 today or tomorrow from the homework. Any administrative questions before we start in on the new chapter? Yeah? Oh, whoops. Yeah, you're right. Why did I say today? Yeah, it's due on April 7th. Sorry. Yeah, okay, what's on the board is correct. So thank you for that correction. 4.3 to 4.4 homework is due on this Thursday. Sorry, I said today for some reason. I have office hours today is probably what I was going to say. Any other questions? All right, cool. Then something that I want to cover really quickly, I just want to recall, okay, something that you should have learned by now, but if you haven't learned it by now, then you definitely need to come to office hours today. But let me just briefly recall what summation notation is. Okay, so I'm going to be writing things on the board which look like this. Okay, we do this big sigma, and then we put something underneath like I equals 1, and we put something on top like whatever, and then something to the right of it, which is going to be the rule for the sum. Okay, so here's what it means when I write something like this. Okay, what I'm going to do is I'm going to add up a bunch of stuff, and what this picture tells me is what I am going to add. Okay, so here's what I'm going to do. I'm going to start with I equals 1, and I'm going to allow I to range from 1 to 10, okay, because it goes from 1 to 10, okay. Sometimes it might say 0 to 5, or it might say 0 to 1,000, or something like that. And we're going to let I take all of those values, okay? And then what are we going to do? We are going to take each of those values, which is between 1 and 10, and we are going to plug it into the function, which is written to the right of our sum, okay? So we take each I, like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and we're going to plug it in to the rule, and then we're going to add up all those things, okay? So for this one, it would look like I would do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5, 6, 7, 8, 9, and 10 squared. And I would add up all those numbers. Okay, so this is what this notation means. Are there any questions on the notation of sums before we move on? Yeah.
So you do the action that's like circled by the purple first, and then you add them up?
Correct. Well, what we want to do is we want to take each number from 1 to 10, we want to square it, and then we're going to add all of those numbers up.
Okay.
So yes, we're going to do the squaring before we do the adding, okay? If I was going to do the squaring after I did the adding, then I would write it some more like this. I would write the sum from I equals 1 to 10, and then I would write I, and then I put all of that in parentheses and square it. And that would be, I think, what you're talking about, where you would do 1 plus 2 plus 3 plus ... plus 10, and then take that number and square it. Okay, so I would use parentheses like that if I was going to do the sum first and then square it. But what I want to do is take each number between 1 and 10, including 1 and 10, and plug it in, and then add up all the stuff that I get. Any other questions? Okay, then I'm gonna move on. Oh, I have another example here. Okay, so sometimes it's gonna be written in a little bit more general notation. Okay, so let's say we have a function, f of x equals x cubed, right? And I write the sum from I equals 0 to 2, okay, of f of I over 2 times I. Okay, so let's see how we would do this. Here's what we're gonna do. We're gonna take each whole number, which is between 0 and 2, okay? So the numbers I have to do are gonna be, I is gonna be either 0 or 1 or 2, right? And what I need to do is I need to take each of these numbers, plug them in for I, right? And then add it all up. Okay, so when I plug in 0, I'm gonna get f of 0 times 0, and then I'm gonna plus, and now comes f of 1 times 1, and then I get a plus, and then comes f of 2 times 2. Okay, so all I'm doing is I'm taking 0, 1, and 2, I'm plugging them into the rule, and I'm adding up. So in this particular case, since I know what f of x is, I'm gonna go ahead and plug in. So this becomes 0 times 0 plus, well, 1 cubed is just 1, so 1 times 1, and then f of 2 is 2 cubed, which is 8, so I get plus 8 times 2. So altogether I get 1 plus 16, which is 17. Okay, so that's just a play example of how we're going to do these summations. Okay, if you want a little bit more review on summation notation and how to do these guys, please come to office hours today, because it's going to be, I'm going to sort of take it for granted going forward so that we can talk about bigger and better things. Okay. So, okay, this is what I was saying earlier. So, you definitely don't need to write all this stuff down, but this is just some stuff that I wanted to say. So, motivation for Chapter 5 is about accumulation of change, okay? So what I mean by that is things like, okay, if I earn $50 a day, then the accumulated change that I might be interested in is in terms of like, okay, how much do I earn in a week? So we take a statement about a rate of change, and we are going to extrapolate that information into a statement about a quantity, a total quantity, or a total change, right? Okay, so we want to ask, how do we find the total change of a substance over a given time period if we know what rate at which that substance is changing? Okay, so if I earn $50 a day, how much do I earn in a week? Or if I drive 80 miles an hour, how far do I go in 1 hour? These types of questions are going to be what we're asking. And then we're going to get a little more complicated with it. Okay, so this one's easy, right? If I'm driving 80 miles an hour and I drive for 1 hour, then I go 80 miles, right? I just take the number of miles per hour times the time that I drove, and I get the answer, right? But what if my speed is changing all the time, right? What if I am speeding up and slowing down and stopping at stoplights and all this stuff? And I have a function which describes how fast I'm driving at a given time period. How then am I going to say how far I went in 1 hour if my speed is constantly changing, right? This is what we're going to study. Okay, so that's the big picture of what we're looking at. And that's all I want to say before we just get right into it. Okay, so we're going to do a little bit of a inquiry-based type thing for a little while here. So we're going to do problem 1 and 2 together, and then we're going to work on problem 3 in our groups. So let's just start with problem 1. So what do we have? We are supposed to suppose that a bicyclist or a cyclist, whatever, travels at a constant velocity of 15 feet per second. Okay, so they're riding their bicycle 15 feet per second for 3 seconds. And we're supposed to compute the total distance that the bicyclist travels over her 3-second trip. Well, we know that there is a relationship between distance and time and velocity, right? We know, for example, that the velocity is going to be equal to the distance traveled divided by the time, right? So, what are we trying to figure out? We're trying to find the distance, right? And we know the velocity and we know the time, right? So if I wanted to solve for the distance, if I know the velocity and the time, I just multiply both sides by time, and I get d is equal to the velocity I travel times the time that I spend traveling that velocity, right? 80 miles an hour times 1 hour, 80 miles, right? So in this case, we would get 15 feet per second times 3 seconds. So the units of seconds are going to cancel out. And I'm going to take 15 and multiply it times 3. And I get 45 feet. Okay, so this is so far hopefully familiar. Okay, so let's just move on. Okay, the second part says we should sketch a graph of the bicyclist's velocity in feet per second as a function of time in seconds. Okay, that's not too hard. So we're gonna make a graph here. Oh, that's not right. There we go. Okay, so time always goes on the horizontal axis, and what's gonna go on the vertical axis is the velocity. Okay, so I'm gonna put velocity here. And what is my picture going to look like if I travel with a constant velocity of 15 feet for 3 seconds? Linear. And what slope? Positive? What's the slope of my linear function going to be? Remember, what am I graphing here? It's the velocity that I'm graphing, right? Is the velocity going up or down? Yeah, it's not going up or down at all. It's just chilling at 15, right? So here's 15. And here's 1, 2, and 3 seconds. Oh, that's not very good. 2 and 3. So what happens is the cyclist travels 15 feet per second for exactly 3 seconds. So this is the graph of our velocity function. And now here's a question. We want to ask, how does the distance that we found in part A manifest in this graph? So, we found out that the distance traveled was 45 feet. Can someone tell me a geometric interpretation of how we see the quantity 45 feet in terms of this graph? Yeah, Alyssa?
It's the area under the line.
Yeah, it's the area, okay? If I were to fill this in like a box and find the area of this guy, okay, then I would get 45, right? So we recognize that the area underneath the velocity function is telling us something about the total change in distance, okay? So this is the fundamental basis of what integration is going to be all about, is checking how do we find accumulated change. Well, accumulated change is going to be represented as the area under a curve, and we're going to develop all sorts of techniques for how to find that area, right? So it's the area is the area under v of t from 0 to 3. I'll say t equals 0 to t equals 3. Okay? So we have a point where we start counting and a point where we stop counting, right? We don't just carry this on forever. We're only interested in the first 3 seconds of the trip. Okay. Any questions on problem number 1? Okay, I'll do one more slightly complicated one. We'll do it together, and then there will be a third, even more complicated one that I'm going to set you loose in groups for. Okay, so suppose a cyclist we're going to change the way that they're doing the trip. Okay, they travel at a constant velocity of 5 feet per second for 2 seconds, and then at 15 feet per second for 1 second. And we want to compute the total distance that the bicyclist travels over her 3-second trip. Well, the total distance is just going to be equal to the distance traveled for the first 2 seconds plus however far she travels in the second, or in the last second. Third second. Okay, so for the first 2 seconds, it's 5 feet per second, and she travels that speed for 2 seconds. So we cancel the seconds again. Okay, and then we're going to add to that 15 feet per second times 1 second. We cancel the seconds, and all in all, we get 25 feet. Right? Because this one, it's 10 feet over the first 2 seconds, and then 15 feet in the last second. All right? So let's draw another graph of the velocity and see how this is manifesting. Here's t and here's v. Okay, so bit of a difference here. Oftentimes when we are drawing graphs of people's trips on a bike or on a car or on a rocket or whatever, we oftentimes put d on the axis here. But here we're putting the velocity. So I just want to point out that major difference. So the velocity is constant at 5 feet per second for the first 2 seconds. So here's 5 and goes for 2 seconds. Okay, and then what happens? Then suddenly, as if by magic, she's traveling 15 feet per second for the third second. Oops. Probably looks like that. Okay, and again, we ask ourselves, how does the distance found in part A appear in the graph? Well, it's just going to be the sum of the 2 areas which are found by taking these 2 rectangles. Okay? So, long ago when you took, I don't know, a math class of some sort, you probably learned how to find the area of shapes which looks like this, right? You just break it up into smaller shapes whose area you do know how to find, and then you find those areas and you add them up, and that's how you get the area of a weird looking shape, right? Or if, for example, if you had a triangle with a circle inside and you want to find what is the area of the shaded region here, what did you do? You found the area of the triangle and then you subtracted the area of the circle, right? To take that part of the area away. Okay, so similar idea is happening here. So again, it's the area of, well, it's the area under the curve again. Only we had to use a slightly more sophisticated technique to find that area, okay? All right, so we're going to do this problem 3 in our groups. Okay, so it's a similar problem, only this time the velocity is a little bit trickier, okay? It's a linear velocity. So let's see if we can come up with that one. in our groups. So I'll be walking around. If you have any questions, just raise your hand, and I'll come help you all out. So go ahead and form groups.
Starting at 5, yeah. Well, yeah, because there's like
I think, yeah.
So from here, right, we want to find the total distance, right? And we have a graph of the velocity, right? So before, what did we do it? We were just taking the velocity that we were traveling and multiplying it times the time that we were traveling at speed, right? But now our speed is going up, so the speed is constantly changing, so we can't exactly do that. But what was the third thing that we recognized that was happening in terms of how the distance was manifesting in the graph? The distance was manifesting in the graph as the area, right? Under the curve. So we've got a curve here.
Me too.
So let's maybe shape in the area under the curve, right? Can we use maybe the new thing we were about the fact that it's the area under the curve to find the distance? We just have to figure out what is the area of that triangle. What is the area of the triangle? Half base times height, right? It's actually 1/2 of a square, right? Because if you drew another one on top, right, we need a square. So you just take the half of it. We
I guess because of that, from this,
But now, the problem is that it's constantly changing, right? So we can't use that technique anymore. This is the idea. But we can use the observation that we made about how is the total distance manifesting in the graph. Is that the total distance is manifesting as the area of the curve. Now, if we were to draw in the area underneath this guy, we would just drop a line right from here down to here, and just shape that in, and what kind of shape you should be. You know how to find the area of the triangle? Well, it's half of the area of the square, right? Because if you were to draw another line this associated with these corrections are pretty easy. Right? So you just take the length times width or height or whatever, and then combine that by 2, you get the triangle. All right, let's go ahead and come back together as a group here. All right, so I saw some excellent pictures out there and some excellent answers out there. So let me just highlight what I saw. So the first thing that I saw most people doing was, well, we should sketch a graph of this velocity function, which of course is a linear function. Okay. So it's a linear function with slope 5, right? So over the course of 3 seconds, okay, when t is 3, 5 times 3 is going to be 15, so it goes up to 15. Okay, so this is kind of what the trip looks like. So initially the speed is 0. So this is like the cyclist is starting from a stop sign and they're slowly speeding up as they go over their trip. Right? They're slowly speeding up. So the tricky thing about finding the total distance here is what we were doing before was we were just taking, well, take the velocity times the amount of time that we travel at that velocity and you get the distance, right? Why doesn't that work here? Yeah, because the velocity is changing all the time, right? So we can't just go ahead and take the velocity times the time. Well, I mean, what's the velocity? It's changing no matter, like, depending on what time we are at. So we need to use a more sophisticated technique, which is we need to go back and remember, okay, this last part of each of these problems was how does the distance we found appear in the graph? Well, the distance in both of these cases was the area underneath the curve, right? So now we've got a curve, and if we want to make an observation or a stretch of our theory, we could say, well, maybe the total distance traveled is going to be the area underneath this curve, right? I just take the area which is trapped between that curve and the t-axis. And how do I find that area? Well, it's just a familiar geometric shape of a triangle, right? So if you forget how to find the area of a triangle, then all you have to remember is that this triangle is exactly half of this rectangle. And I think everyone should remember how to find the area of this rectangle. We just do 3 times 15, right? So the area of the triangle is going to be, the area of the triangle is going to be 1/2 of 3 times 15. So we get 45/2. And that's the area under the curve. So that's going to be a measurement of velocity times a time, right? It's a 1/2 times a velocity times a time, right? So that's how we got this area. So its units are going to be feet. Okay? Because the units of 3 was seconds, and the units of 15 was 15 feet per second. Okay, so this is kind of cool, right? Now we know how to find the distance traveled even when the function is changing all the time. All right, it just came down to finding that area. Any questions on problem number 3? All right. Sounds like people are pretty happy. So based on our observations in problems 1 through 3, write down a rule for finding the total distance traveled by an object with velocity function v of t between times t equals a and t equals b. Well, I think what we want to do is find the area under v of t from t equals a to t equals b. Okay? All right. Any questions so far? No question? All right, then we're gonna learn something a little bit different, which is called Riemann sums. So long ago, this guy named Riemann was adding some stuff up, so they named it after him, I guess. And what was he adding up? Well, Riemann had a question, which was, how do I find the area? I know that this area seems to be important, this area under the curve. And I can do it when the function's like, you know, flat, or I can even do it when the function's aligned, because I can make a triangle, right? But what if the function that I want to find the area under is like curvy or weird? How do I find the area of a shape which looks like this? Now that, I can't even break it up into like smaller pieces that I know how to take the area of, right? So the big question is, how do I find the area of a shape like this? So let me use some extra space down here to draw a quick picture. The way we find the area of a curve like that is actually we don't find it. What we do instead is we approximate it by the following. Well, Riemann said, I can't find exact shapes which I can piece together which would add up and look like this thing, but I do know that if I use a bunch of rectangles, which, let me draw a bunch of rectangles. You know what? Maybe I can even use this shape. Can I use this shape? Oh no, there isn't a shape. But I can do this. Okay, I can use a bunch of rectangles and get something which is like pretty close. Okay, so I'll just do a couple more and we'll just go from A to B. How about that? Okay, so this is A and this is B. So to find the area underneath this curve from A to B, I'm talking about this area which is enclosed by the green stuff. To find that area, Riemann said, I can get pretty close by taking these rectangles and adding them up. Okay, which is not bad, but we could do even better than this by using skinnier rectangles. So what if instead I used these green ones? I'm going to put one there, one here, oops, one there, and one here. Right? The idea is if I use even skinnier rectangles, then the area is going to be even closer to the true area underneath the curve, okay? Oops, that shouldn't look like that. That should look like that, of course. Okay, so if I took these green rectangles, then the area would be even better. Even less error, okay? And this is the whole idea behind Riemann sums, to estimate the area under a curve, okay? So there are a couple things which we need in order to determine what is the Riemann sum going to be. Well, the Riemann sum is the sum of the areas of these rectangles. Okay? And how do we add them up? Well, there's a couple things we need to decide. The first thing we need to decide is how many rectangles. And the second thing we need to decide is how tall is each rectangle going to be. Well, the natural choice is to say for a given rectangle, we're going to take the height of the rectangle to just be the height of the function somewhere in that rectangle's interval. Okay, and we're going to get a different rectangle depending on if we take the height of the function on the left side of the interval or if we take the height of the function on the right side of the interval, or somewhere in between, right? So this is how we're going to choose the height of the rectangle. Okay, and the two most common ones are called a left Riemann sum and a right Riemann sum. Those are the ones where we take the height of the rectangle to be the left side of each subinterval. Okay, so the area under f of x from x equals a to x equals b can be approximated using n rectangles, parentheses. If we have n rectangles and they all have the same width, then we have to fit n rectangles between A and B, which means that the width of each rectangle, which we denote by delta x, is going to be equal to, well, we take the total distance which we have to cover and we divide it by the number of rectangles that we have. And that's going to be the width of each rectangle, okay? D minus A over N. Okay, so a little bit of notation here. The A and the B are always the leftmost point at which we start the counting area, and the B is the rightmost point at which we stop counting area. The N is the number of rectangles we are going to use, so N for number. And the delta x, okay, is a change in x. Now, x is always on the horizontal axis, right? So if we talk about a change in x, we're talking about a distance which looks like this, right? And that is going to be if we talk about a left and right distance for a rectangle, then we're referring to that rectangle's width, right? So, what do we want to do now? Okay, so area under f of x from x equals a to x equals b can be approximated using n rectangles of width delta x equals b minus a over n, using either a right Riemann sum Okay, now what does a right Riemann sum look like? Well, we take the height of the function on the right side of each interval. So the first interval goes from a to a plus delta x, right? So the first height that we choose is going to be the height of the function on the right side of that first subinterval, which is going to be the height of the function at a plus delta x. So the height of that first rectangle, okay, why can I not move the screen? The height of that first rectangle is of course going to be just a f of a plus delta x. And what is the width of that rectangle? The width of it is just delta x. So we take f of a plus delta x plus times delta x, and then we plus, and then the next rectangle is the interval which goes from a plus delta x to a plus 2 delta x. And we take again the height of that rectangle to be the height of the function on the right side of that subinterval, which will be f of a plus 2 delta x. So now we go plus f of a plus 2 delta x. That's the height of the second rectangle, and the height of the second rectangle, or the width of the second rectangle, is the same as all the others, delta x again. So far I've added together the first two rectangles of my sum, and now I need to know, okay, I'm going to keep going on like this. I'm going to keep adding stuff, and when do I stop? Well, the very last rectangle, okay, is going to be the rectangle which goes from b minus delta x to b. That's the last subinterval. So if I take the last subinterval, I know that the height of that rectangle is going to be, again, the height of the function on the right side of that subinterval, which is what I get when I plug b into the function. So I get a bunch of intermediate terms, and then finally the last one will be f of b times delta x. Okay? So, the way we write this using summation notation is as follows. We could do the sum from I equals 1 to, let's see, I want n here. I equals 1 to n of, what do? I take the function and I plug in a plus whatever I is times delta x. And I multiply by delta x. Okay, so this sum is going to be taken from I equals 1 to n. So I have n rectangles. So I do this process n times. I take f of a plus 1 times delta x. Then I do f of a plus 2 times delta x. That gives me the second term, right? And I do that all the way up until n. When I add n times the width, b minus a over n, to a, then I get b minus a over n times n plus a is just b, right? So that's how I get the very last rectangle. Okay, now this is really kind of notationally heavy, so I don't want to get too caught up in the details of this formula. All I want to say is we need to take n rectangles, a certain number of rectangles, and fit them between a and b. And the way we pick each height is going to either be maybe the height on the right side or the height on the left side, or two other ones that we're going to see in a minute, but I don't want to overload you. So how are we feeling about right Riemann sum so far? Are there any questions? Yeah, Brendan.
So for the last term, f of b,
Mm-hmm.
You wouldn't add anything to that because that's the last, that's the last rectangle.
Exactly.
Okay.
So it's the last rectangle. So the last rectangle should be landing here, right? I know this is the width and this is the location that it's going to be. I just need to pick how tall is it going to be. So if I'm using a right Riemann sum, then I'm going to pick the height on the right side of that subinterval. If I was using a left Riemann sum, then I would pick the height on the left side of that subinterval, and that is going to change things slightly. Okay, but we wouldn't want to go past b, right? Because then we'd be taking a height somewhere over here, which is not going to be relevant for the area which is, underneath here, right? If we took a height that was elsewhere, it has no bearing on that area. So we should always choose our heights somewhere in our interval. Okay, now, if I'm going to tell you about a right Riemann sum, I should also tell you about a left Riemann sum, which is basically the same, only instead of taking the first height of the rectangle to be the height on the right side of the first subinterval, I'm going to pick the height of the first rectangle to be the height of the function on the left side of the first subinterval, which is nothing but what I get when I plug in a into the function. So this one is going to be f of a, not plus anything, just f of a times delta x, plus f of, the second one is going to be a plus delta x times delta x, plus ... And when should I stop? Well, I should stop at the last rectangle. And the last rectangle goes from here to here, and if I take its height to be the height on the left side, okay, the height on the left side, then I've gone almost all the way to b, right? I know each width is delta x, and I go over, if I go delta x n times, I get all the way to b. So if I go one less than that, I get to the point where I want to be. So the last term in this sum is going to be f of a plus n minus 1 times delta x. Times delta x. Okay, so I go over at exactly n minus 1 many rectangle widths. Okay, so how does that one look? It looks like this red one that I put here. Okay, so what's the difference between these two? Okay, well, first of all, I put the delta x on the other side, so let me make that consistent with the other one. So the difference here is this time, instead of I going from 1 to n, we use the exact same formula, only I is going to go from 0 to n minus 1 for a left-hand sum. Okay, so the first term is what we get when we plug in 0 for I. If I plug in 0 for I, then this part is just going to go away, and I'm going to be left with just f of a, which is the first term in the sum where I've written it all out, right? Okay. So the things which I really want to remember for this part, okay, are especially the a, b, and the delta x and the n and how they fit together, okay? The way they fit together is via this relationship. Delta x is b minus a over n, right? That's the width of each rectangle. If I take n many rectangles to cover up a space which is n units long, right, then I just divide it equally between each of the rectangles, right? So each of the n rectangles has exactly this width. And then when I add up all of their widths, I will get the entire interval. Any questions so far? We're going to see lots of examples. Okay, so I just want to remind everyone also that this is an approximation, right? This is not going to give us the true area under f of x. This is going to give us an approximation of the area under f of x. But we do know that when we use lots and lots of rectangles, i.e. when n is really, really big, then the area is going to be pretty dang close, okay? In fact, it's going to be as close as we want. That was Riemann's big discovery. Okay, so one more thing I want to talk about is an upper versus a lower estimate. Okay, for an upper estimate, or an upper Riemann sum, sometimes it's called, it's just another strategy for how to pick the height of each rectangle. We pick the height of each rectangle to be the highest value of f of x when x is in that particular subinterval, i.e. x is in x plus I delta x, comma, and I'll take a bracket, comma, x plus I plus 1 times delta x. Okay, so how does that look like? It just looks like if we have a function which looks like this, okay? And let's say we're using 3 rectangles going from A to B. Well, the way I pick the height of the first rectangle is I take a look at the first subinterval, and I look for the highest value of f of x in that subinterval. It looks to me like it occurs at the right side of this interval, so that's how I'm going to choose the height of the first rectangle. It's just the tallest point in that subinterval. Then for the second one, I'm going to do the same thing. I'm going to pick the highest point, which looks like maybe it occurs somewhere in the middle of that subinterval. So I'm going to take that highest point and I'm going to extend it to the right, and I'm going to extend it to the left. Okay, so the subinterval, the height of the rectangle isn't necessarily the height on the right or the left. It's the height which maximizes the height of that rectangle. Okay, then for the last one, I take the last subinterval. I look for the point on this last subinterval where the function takes its highest value. This time it happens on the left instead of on the right. So I'm going to take that point and I'm going to extend it over. And I'm going to take this to be the height of the third rectangle. Okay, so rather than taking the height just on the left or just on the right, I take whichever height is the biggest. And the reason it's called an upper Riemann sum is because if I do this, then all of the error, okay, the error which is causing my approximation to be a little bit off, is going to be above the function itself, which means that if I add up all the areas of the green rectangles, it's going to be bigger than the area which is under the curve, okay? So I get an overestimate, right? You can think of situations where you might want to overestimate something, right? Like I might want to overestimate how much fuel I am going to need to do a certain road trip, right? Because if I do an underestimate, I might run out. I might get lucky or I might run out. But if I have an overestimate, then I'll definitely make it. Okay, so this is how we get an overestimate. So let me also just say, okay, this part here is a plus delta x, right? And then the next interval goes from a plus delta x to a plus 2 delta x. So that's a plus 2 delta x. So, and then the interval from a plus 2 delta x to a plus 3 delta x gets us all the way, the rest of the way to b. So this is how we do an upper estimate. Okay? And I'll just say similar for a lower estimate. Only except, guess what? Instead of picking the height of each rectangle to be the highest, okay, we're going to pick the height of the rectangle to be the lowest point of f of x in that subinterval. Okay, so for a lower, maybe what I'll do is I'll make this purple. That would be cool. I'll make that purple, and then I'll draw what would the purple look like. It would look like this, right? That would be the lower estimate. Take the smallest point on each subinterval, and I would get a lower estimate, right? So that's a situation where I would be underestimating the area, right? When might I want to underestimate the area? Well, maybe I'm trying to figure out how much money do I need to be able to buy all the supplies I want. Wait, no. I would want to overestimate again there. When might I want to underestimate? I want to underestimate if I'm going to underestimate how much money is going to come into my company, right? I might want an underestimate for that purpose, because if I think I'm going to get more money than I actually do, that could cause me some problems. So various situations where we might want to under or overestimate a quantity. So these are 4 ways to do a Riemann sum. The first way, just pick the height on the right side. The second way, just pick the height on the left side. The third way, just pick the highest point in the subinterval. And the fourth way is just pick the lowest point in the subinterval. So these are 4 ways to do Riemann sums. We've really seen it all. So let's pause before we do an example and see if there are any questions on these 4 different ways of doing Riemann sums so far. Yeah.
So if the curve were flipped and they were facing like an upward facing parabola, would that change anything, or would we still want to take like the upper or lower Riemann sum depending on what we're trying to find?
If you want an underestimate, you always use the lower Riemann sum.
Okay.
If you want an overestimate, you always use the upper Riemann sum. And a left or a right, depending on the curvature of the curve, could be an over or an under, or it could be even exact. It just depends. You know, there are a couple other quadrature rules here, like midpoint rule or trapezoidal rule, where you do this slightly differently. But these are the 4 ones that we're going to worry about. Okay, so, I don't know what this is doing here. This is just floating randomly. Okay, so let's do some examples. So we'll do this one together. So we consider the following problem. We have a car moving with an increasing velocity, and we measure that car's velocity every 2 seconds, obtaining the data in the following table. Okay, So the velocity is going up 20, 30, 38, 44, 48, 50, right? So we want to ask the question, how far has the car traveled? Only we don't even have a good picture of what the graph of this thing looks like. We could draw an approximation. Let's go ahead and do that. What we have in terms of information is, okay, 0, 2, 4, 6, 8, and 10. And these are what? Seconds? This is time in seconds. And then our velocity is in feet per second. We need 20 to 50. So here's 20, here's 30, here's 38, here's 44, here's 48, and then 50 is right next to it. So what does this look like? Well, it just goes like this, right? Steadily marching up. Okay, but as for what this function looks like in between, we have no idea. It could look like, this, or it could look like this, or it could look like, whatever. It could look like anything. We're not sure, okay? Or it could look like this, right? I mean, it probably couldn't look like that, just physically speaking, but you get the idea. We don't know what the function looks like. But we still want to know how far did the car travel. So we're going to estimate the area under this curve using the best information that we have, right? Which is, how fast was the car traveling at various endpoints, right? Okay. So let's not get ahead of ourselves. Let's read what the problem is asking us to do. It says, the distance is equal to velocity times time. The car travels at least 20 feet per second times 2 seconds in the first interval. So the first subinterval goes from 0 to 2 seconds, and we're traveling at least 20 miles an hour during that interval because we know that the velocity is increasing. So what is the shortest distance that the car could have traveled in this first subinterval? Well, the slowest that the car is driving in that subinterval is 20 feet per second, right? So the slowest that the car could be going would be like this, right? But more likely the function looks something like, this, right? The car is steadily increasing in speed. But we know that the area underneath this pink curve is going to definitely be more than the area underneath this red line. Okay, so the underestimate, hello, that's a big thunder. Okay, so the area underneath that guy is just gonna, of course, be 20 times 2 equals 40 feet, right? That is the smallest amount of distance that the car could have traveled in the first section. Oh, then we're supposed to say in the next 2 seconds. Well, in the next 2 seconds, an underestimate for the car's speed is again, whatever the speed was at the start of that interval. We know that that's an underestimate because we know that the function is increasing, right? So another underestimate for that would not be 20 times 2, but rather it would be the lowest height that this function could be in this interval is 30. So you can tell we're doing a lower sum here, right? 30 times 2 is 60 feet. Okay, so how do we actually find the shortest distance that the car could have traveled during the entire 10-second period? Well, we're just going to keep repeating this process. Okay, we have 5 subintervals, right? 1, 2, 3, 4, 5. And for each subinterval, I'm going to make a rectangle. And the height of the rectangle is going to be the lowest possible height of the function on that subinterval. So if I know the function's always going up, then the lowest point in each subinterval is always going to be the one on the left. So I get something which looks like this. Okay, and in fact, I don't end up using the last data point here where the height is 50, do I? I don't even use that. All I do is I use all the points which are on the left to determine what is the height of each rectangle going to be. So if I want to find the area under the pink curve, I say that the area under pink curve is approximately equal to 20 times 2 plus 30 times 2 plus, I'm going to do 38 and 44 and 48 for the last three. So 38 times 2 plus 44 times 2 plus 48 times 2. Okay, where each of these is corresponding to one of these rectangles, right? 38 times 2 is corresponding to the area of this rectangle. And 20 times 2, right, is corresponding to the area of that rectangle. Okay, so can you guys see all of that? So the areas here, all we're doing is summing up some areas. Okay, so if you don't, like using the summation formula, you don't have to use it. You just need to make sure that you know how to divide up that area into equal widths and find the height of each rectangle, and then from there it's just adding up some length times widths, right? Okay, questions on part A and part B. So we found the underestimate on the shortest distance that the car could have traveled during the entire 10-second period. Yeah.
So this is essentially finding the max, but rather than focusing in on a micro level scale for looking outwards?
Well, I'm not sure that this has much to do with like the min-max theory that we were talking about in the previous one, right? Because that's talking about the derivative of a function, right? You want to find the maximum of a function, then you're going to have to do your global min, global max search. And in that scenario, you would already have the pink curve or something like that, and you need to find its derivative, find where it's equal to 0, and that stuff. But what we're doing here is we're just providing an underestimate. We're underestimating the area which is shown in green here. We want to find a lower estimate, and we say, well, if I add up all the areas of the red stuff, it's going to be close to the area under the pink, where it's circled in green. And I know not only is it going to be close, I know it's going to be less than the true area under that pink curve. Does that make sense? Did I answer your question?
Yeah, so I guess then it's more like the opposite, because instead of like looking inwards, you're looking outwards.
Yeah, it is going to be generally an opposite type of a thing, because what are we doing here? This is a graph of the derivative of a function, and we're asking a question about the function itself, right? Velocity is the derivative of the distance function, and we are asking what is the distance. So we have the derivative. We're asking something about the parent function. So it isn't working backwards in that sense. Okay, let me ask, is it clear how I chose the height of each rectangle in this circumstance? Why couldn't I choose the height on the right side of each subinterval?
The max?
Huh?
Be the max.
Yeah, then it would be the max. And it would be the max specifically because this is an increasing function. They say in the problem it's increasing, so I know it's going up as we go from left to right. Very good. Okay, so I think it's important to see lots of examples of these guys, so let me do some more before we run out of time. Car travels, what is the greatest distance? Okay, how do we do the greatest distance? Well, the greatest distance is going to be where we pick. Okay, I don't know why. Sometimes I just cannot move the screen. That infuriates me. The greatest distance is going to be, like Eli said, it's going to be the height on the right side of each subinterval. So I'm going to take rectangles which would look like this instead. And you can see that all the error for the green ones, right, is above. All the error for the green ones is above. So if I add up all those green areas, I'm going to get something which is bigger than the area under the pink curve. So if I were to do this using those guys, I would do instead of 20 times 2, I do 30 times 2. I'd pick 30 times 2 plus 38 times 2 plus 44 times 2 plus 48 times 2, and then I would have an extra one on the end for the 50 times 2, right? So it's just a matter of difference. I still have 5 rectangles. The only thing that has changed is how am I choosing their heights, okay? Any questions about, I mean, I know it's really hard to see that. Why don't I zoom in? Is there any questions on how I chose the upper sum heights? Yeah.
Let's do for part C.
Well, for part C, okay, it says, what is the greatest distance? Oh, yeah, sorry. What am I doing? So yeah, part D says, now that you have an underestimate for part B and an overestimate for part C, what would you say is a good estimate for the total distance traveled by the car? Probably somewhere in between. Okay. I want to make sure that I get to a couple more examples, so I'm going to move on from this example. If you still have questions on it, please come to office hours, because I should show you at least one other one here. Okay, why don't we do... I'm going to make one up. We're going to do a left Riemann sum to approximate area under f of x equals x squared from 1 to 4 using 3, actually why don't I say using 3 rectangles. Okay, so how do I start a Riemann sum? The very first thing that I always do is I identify. Hopefully we don't lose power, because if we lose power, the lecture's over. I'm going to identify A, and I'm going to identify B, and I'm going to identify N. Okay, so I've got A, B, and N. And the last piece of the puzzle is, of course, delta x. Can anyone tell me what the width of each rectangle is going to be if I go from 1 to 4 and I use 3 rectangles? 1, right? Because I go from 1 to 2, and then from 2 to 3, and then from 3 to 4. And I get that number by doing the length of the interval, that's b minus a, and I divide it by the number of rectangles I want, which in this case is 4 minus 1 over 3, which is 3 over 3, which is 1. So I know the width of each rectangle is going to be 1. So if I want to do a left Riemann sum on this guy, how am I going to do it? First thing, I like to draw the picture of what I'm doing. So this is what the function f of x equals x squared looks like, and I'm interested in what the area is from 1 to 4. So from 1 to 4. So I want to know, what is this area under this curve? Right? That's what I want to know. So I'm going to estimate it using a Riemann sum. I know that the interval, the width of each rectangle is 1. So I'm going to put on some extra marks here to mark where are my intervals going to go from. Well, I'm going to have one from 1 to 2, one from 2 to 3, and one from 3 to 4. And the height of each rectangle is going to be, since I'm using a left Riemann sum, I'm going to use, for each subinterval, the height of the rectangle on the left side of that interval. So for the first one, it would look like this. And the second one, it would look like this. And for the last one, it would look like this, right? So I think drawing a picture is always really helpful for this. So if I want to actually find out what this Riemann sum is, all I have to do is take these areas and add them up. Well, the Riemann sum, left Riemann sum, is going to be equal to the height of the first rectangle times the width of the first rectangle, which is, the way I get the height is I take the point which is on the left, which is 1, and I plug it into the function to get the height. That's 1. So 1 times the width is also 1. So I get 1 times 1. Then for the second one, I ask, what is this height? Well, the way I get that height is just by plugging 2 into the function. So I square it, I get 4 times 1 is the width of that rectangle. And the last rectangle, its height is the height of the function on the left side of the interval which goes from 3 to 4. The height of the function on the left side of the interval which goes from 3 to 4 is just whatever I get if I plug 3 into the function x squared, which is 9, times the width of that rectangle is also 1. So I get 1 plus 4 plus 9, which is 14. Okay, so this is an approximation of the area shaded in yellow. Now, it's got a decent amount of error in it. If you just look, we're missing all of this yellow part and this yellow part and this yellow part, right? So we're missing a lot of the area. In fact, we can determine whether we have an over or an underestimate by checking. We can see all of these are all underestimates, right? For the given region that it's trying to capture. So this is going to give us an underestimate on the area underneath the curve f of x equals x squared from 1 to 4. Any questions on this example here? Okay, I know we're running a little low on time, but I want to do one more quick example here. You know, if you really got a dash, then go ahead and leave. But I'm going to take a look at this one. Maybe not this one. This one's too long. Why don't I do one right Riemann sum? Let's do a right Riemann sum. Same function, f of x equals x squared from 1 to 4 using, this time we're going to use 4 rectangles, okay? 4 rectangles. Well, the first thing I'm going to identify is this is my A, this is my B, and my N is 4. So I know that my delta x is going to be 4 minus 1 over 4, which is 3/4. Okay? So now my picture is going to look a little bit different. First of all, it's going to look different because I'm using 4 rectangles of width 3/4 instead of 3 rectangles of width 1. So the first thing I need to do is go to 1.75. Okay, and then I move over by another 3/4, so I add 0.75. Then I'm at 2.5. Then I add 7.75, and I'm at 3.25, and then I'm at 4. Okay, so now I'm switching it up a little bit here. There's no rule which says that the width of each rectangle has to be a whole number. In fact, we don't want it to be. Eventually, we want the width of each rectangle to be teeny tiny. So the way I'm going to choose, doing the right Riemann sum, I'm going to choose the height of each rectangle to be the height of the function on the right side of each subinterval. So I want this area, so I'm going to choose my heights as follows. This time I choose the right side of the first interval, and I extend that rectangle over to the left. And then again, on the right side, extend it to the left. And then again, on the right side, extend it to the left. And then finally, on the right side, extend it to the left. And from here, it's literally the same process. We just add up these heights. Well, the height of the first one is 1.75 squared times 3/4. That is the width of the rectangle, right? The second rectangle has height 2.5 squared and width 3/4. The third one has height 3.25 squared and width 3/4, and the very last one has height 4 squared and width 3/4. Okay, so we add all those up and you get a number. But I just wanted to give you a quick example of the difference between a left and a right Riemann sum. We're going to do lots more practice with this. Thanks for your attention. I have office hours today. If you have questions, please come. Otherwise, I'll see you on Thursday for the quiz.